Let's look at periodic orbits and special periodic orbits called limit cycles. So periodic orbits are solutions such that it exists a time t, capital T positive, such that after capital T time, you're back where we were before. So in this case, we have x at t is equal at x as capital T plus t. Then we say that x is periodic and it is of period capital T. Let's try to find an example. Oh, sorry about this. Let's try to find an example. We have this system, x dot y dot equals x plus y minus x times x squared plus y squared. And in the second line, we have minus x plus y minus y times x squared plus y squared. Linear approximation at the critical point 0, 0 gives us an unstable spiral. But if we look at this a bit longer, so at 0, 0, we're only taking into account the linear terms. So we're only taking into account for the derivative of x plus y, and for the derivative of y, minus x plus y. But then we look at the nonlinear terms, and we notice that as x squared plus y squared times minus x or times minus y. For x and y sufficiently big, those terms are really important. We expect those terms to become more important than the linear terms. That means that for x very big, what we are expecting is something like this. For our direction field tending to the origin. Because x squared plus y squared is just something positive and big, and we have minus x and minus y, so something that is tending to the origin. In the center, we have an unstable spiral going away. That means that somewhere in between, there must be a change between the unstable spiral that is pushing us away from the origin and the behavior very far from the origin that is pushing us towards the origin. So in the middle, something must happen. In order to find what happens, let's change the polar coordinates. I mean, we have that term x squared plus y squared that should hint to us that maybe polar coordinates are the way to go. So we are establishing x equals r cos theta and y equals r sin theta. Then we will try to find out the derivative of r without going crazy on the change of coordinates. So we consider r squared equals x squared plus y squared. That means that if you take the derivative with respect to time on both sides, you have 2r times r dot equals 2x x dot plus 2y y dot. We forget the 2, but we know x dot and we know y dot, so we can just plug this information in, and we retrieve that r dot is equal to x squared plus y squared minus x squared plus y squared, all of it squared. We do some changes around and we retrieve r dot equals r squared times 1 minus r squared. We simplify for r because we know r is always positive. And here we find that r dot is equal to 0 for either r equal to 0. We knew that, that's a critical point. But also for r equals to 1. That means that in our faceplate, things are moving towards the radius, the circle of radius 1, both from the origin towards it and from outside towards it again. What can happen on that circle of radius 1? Well, you could get stuck on it and not move anymore. But if you're moving all the time, it needs to be a periodic orbit. So you could have some odd critical points on this circle, in which case you wouldn't have any periodic orbit. But if you don't have any critical points, you're just circling around this circle all the time. In order to figure this out, what we need to know is theta dot that we haven't computed yet. So again, going back to our formulas for the polar coordinates, we have x equals r cos theta, y equals r cos theta. So if we take the derivative of the first equation with respect to time, we have the derivative of x with respect to time is equal to the derivative of r with respect to time times cos theta, plus r times the derivative of cos theta with respect to time, that is minus r sin theta times d theta dt. And something similar comes out for dy. And what we do is we multiply the first equation by y on one side, that is equal to r sin theta, and the second equation we multiply by x, that is equal to r cos theta. In this way, the first terms, dr d theta cos theta and dr d theta sin theta, become the same thing. So we can subtract these two equations and hope that the terms we don't like are going to simplify away. It actually happens. So if we take y dx dt minus x dy dt, the first terms, dr dt cos theta and dr dt sin theta, cancel out for each other, and we are left with minus r squared cos theta squared plus sin theta squared times d theta dt. But cos theta squared plus sin theta squared is equal to 1, so that simplifies away. That means that minus r squared d theta dt is equal to, well, y dx dt minus x dy dt. We can plug in the information about dx dt and dy dt, and that simplifies to x squared plus y squared. That is equal to r squared. So if we simplify again, we have that d theta dt is equal to minus 1. What does this mean? It means that all the time, theta is just decreasing linearly. That means that if we are on the circle of radius 1, r is not changing because r dot is equal to 0, but theta dot is constantly changing in the negative direction. That means that we have found a periodic orbit. Not only that, we also know that everything inside this periodic orbit is moving towards it, and everything outside is moving towards it as well. So as time tends to infinity, everything nearby tends to the periodic orbit. This is what we mean by limit cycle. The system limits to a cycle. Limit cycle is an asymptotically stable periodic orbit.